And this is the first crowd, I think, that my Idiot's Guide to String Theory has not drawn peals of laughter from, so I appreciate you on that. When actually we developed a title for that book, a lot of the string theorists said, yep, that's a very good title because we feel like idiots when confronted with our own theory. Anyway, I can't believe it's been 4 some odd years since I was at the CQT. It feels like yesterday. It's amazing how time flies. I had a lot of fun talking physics with people, eating with people. I think were you there when we did that paintball or laser tag match? Anyway, we did all sorts of crazy things, and I know you guys are capable of doing crazy things around here. And out of the discussions that I had in that time came several blog posts, came the beginnings of this book project and my research and thinking about that, and actually the beginnings of a Scientific American feature article came out of that. So one of the goals I have in this book is to synthesize different areas of physics. What got me interested in writing on this topic of non-locality and its many guises was hearing that word in many different contexts. So it wasn't just quantum foundations and quantum information and quantum optics, but you also hear it a lot in gravity theory, both classical and quantum gravity. You hear it a lot in quantum field theory. And I got to thinking, well, what are the relationships among the phenomena that are at least deemed non-local in these different areas? And my proposition, or maybe my working assumption, is that each area can inform the other areas. And I will be talking about entanglement today, or kind of an interpretive level. So quantum information can offer help with problems in quantum gravity. I think that's kind of a surprising idea, but that's really been developed in recent years because of the tools that you guys have really developed to characterize entanglement and understand it. Quantum gravity can help out with problems, one would hope, in quantum information theory, certainly a lot of the interpretive questions, but also just knowing the range of physical phenomena over which entanglement and the structure of entanglement is an important issue. I think just as a kind of, when you step back and gain some perspective on things, it's just kind of just amazing that you can use gravity theory to describe networks of entanglement. I mean, who would have thought that 15 years ago? And that you can use quantum computation, quantum complexity theory, quantum error correction to understand black holes, which seem also kind of a very surprising connection. So I'm just going to put up this blank screen because I'm going to talk for a little bit before I go into some of my slides. But before I begin, I want to give a few disclaimers. I come to you with some trepidation to experts in the world on these questions, and I'm simply a mere humble science journalist trying to make sense of them myself. So bear with me on this. It's not going to be a technical talk, really. My interests are really in interpretational questions. And as you know, interpretational questions are the minefield in this field. Everyone, you put 2 physicists in a room, they have 18 interpretational ideas, and they'll argue. The same physicist would argue to him or herself about these interpretational questions. So it's kind of difficult sometimes for someone like me from the outside coming in. And I welcome your guidance on those kinds of questions. I also know that the words local, the word non-local have vastly different connotations, even to different people, but certainly within different domains of physics. Obviously, you can talk about Bell locality, relativistic causality, separability of states, and there's different meanings of these terms. And as part of my kind of synthetic project, I take a very broad view of these words. And I do think there are relationships in how these words are used in the different areas of physics. And I think it's fun to explore what those relationships might be. And as my guiding light in this, I really take Einstein himself, who took a very broad idea of what the words, I didn't actually, I think, use the word locality, but he took a very broad idea of what we now call concepts of locality and non-locality. For him, actually, was a package of concepts, any one of which, if failed, would bring up huge interpretational problems for physics. Finally, I know that the word spooky action at a distance rubs a lot of people the wrong way, and partly it's a marketing thing, I'll admit it. You sell more books with the word. But also, I'll say that I'm not a Bohmian, so I do think that there's no causal action at a distance within physics. And if there were, we should be able to use these entanglement phenomena to send signals, and we can't, so probably nothing like action at a distance in the sense of a Newtonian gravity theory, for example. Nonetheless, we're faced with some deep questions about how to explain correlated measurement outcomes. If the measurement outcomes are indeterminate, what do we do to explain those if we're not going to resort to action at a distance? And that's obviously the big interpretational question that we face. So the point of contact between the fields of quantum information and the fields of quantum gravity, which are the two fields I'm going to try to bridge a little bit today, the point of contact between them interpretationally is that we should, or we seem to be forced to, go beyond classical notions of space-time. That somehow space-time being the foundation of all the physical sciences, going all the way back to, well, Newton certainly, and going back really to the Greek atomists, Aristotle as well, that space-time is how we describe our physical theories. They're formulated, for the most part, within space-time. We index objects, we index properties in field theory, for example. But it's important to remember that our notions of space-time are an inference. We see phenomena in the world, and we seem to be able to account for those phenomena by locating processes and mechanisms and properties and objects in space-time. But it's always an inference. We don't really see space-time directly. We infer it. So therefore, if we see phenomena that aren't fitting into that framework, we should feel free to discard all the great work of Democritus and Aristotle and Newton and all the rest. We should take that step, and I think that is the step that may be forced upon us today. That's at least going to be the proposition that I'm defending, acknowledging that there's a lot of controversy around it. It's not just, by the way, entanglement phenomena. It's a Aharonov-Bohm effect. It's the kind of relationalism that you get in general relativity theory, the kind of Machian ideas that inspire general relativity theory and other areas of physics. So when I use the word non-local in my very broad sense of that term, I'm really have in the back of my mind that I'm actually using it as a synonym for spatial or spatial temporal. So when we use the word non-local, it's tantamount to saying that there are phenomena in the world that cannot be situated in a spatial temporal framework. And I'm hardly the first person to argue this. Here's just a series of quotes that I was able to fit onto one slide from people on both in quantum gravity and in quantum mechanics and in quantum information theory. A lot of people have argued over the years that we need to go beyond at least a classical or semi-classical space-time framework to understand a lot of the phenomena that we look at. In other words, this is the way to de-spook quantum physics, to take the spookiness, so-called, out of it, and to give some kind of rational explanation for it in the context of going beyond space-time. One of my book reviewers had a really great way of putting it. I wish I had has presence of mind to say this. When we see what we think is spooky action at a distance, what we really have is spooky distance that's being revealed by its action in the world. So that's coming more from the side of quantum foundations and quantum information theory, but from quantum gravity, it's been thought actually for exactly 100 years. Einstein in 1916, so the ink was barely dry on general relativity theory. I don't think the Schwarzschild metric, Karl Schwarzschild had even developed that, so a lot of the ideas of general relativity were very fresh in people's minds. Einstein wrote to a friend, and he said, oh my God, these new ideas of quantum theory, and quantum theory was, I guess, just old quantum theory in those days. It was barely even a theory deserving of the name. I think quantum principles are violating or in tension with, at least, this brand new theory of general relativity that I've developed. So he recognized very early on that we would have an issue in understanding quantum gravity. In other words, we'd have to go beyond the space-time manifold, is actually how he put it. Now, pretty much all the string theory, and having written a book about it, I can assure you that there's vehement disagreements within the quantum gravity community on pretty much everything from where to go for dinner to what theory and what theoretical constructs to use. You don't want to get Brian Greene in the same room as Lee Smolin. I mean, a lot of these things are very contentious. But I think all of the people in these different areas of quantum gravity would agree on one thing, namely that we need to go beyond classical, semi-classical ideas of space-time, that somehow space-time, as we see it around us in the low-energy world, is derived from something, and it's not clear what it's derived from. The usual picture and this is from a kind of an old article going back to the early 90s, an old popular level article, is the usual picture is something like this, that we see space-time. This box represents, or maybe just space in this case, but space-time. and it's a featureless entity as far as we can turn. We can tell it's a manifold, it's curved, et cetera. But if we zoom in, we begin to see a quantized or some kind of filigree structure, maybe down at the Planck scale. And that's kind of the idea that animates quantum gravity, that you go down far enough, the quantum fluctuations start to muck up the geometry and even the topology of space-time. Now, if you go the other way, if I were actually run this animation backwards, you'd have a problem of taking the low energy limit of this kind of thing and trying to recover the space-time that we observe. And that's kind of an issue, because it can't be as simple as taking, for instance, Heisenberg even had an idea of basically a chessboard-like space. And we can kind of zoom out from the little individual chessboard lattice cells and pull back. We don't see the individual lattice cells, we just see a smooth space-time, but that causes a lot of issues as well. So I think today, people take more of an idea of emergence. Namely, the individual quanta of space are not themselves spatial, just as a fluid is not present at the molecular level. You have to pull back and get the collective properties such as flowing, surface tension, wave propagation, et cetera. So here is a toy model for that. If you're not familiar, it comes from a very toy model called quantum gravity, with spelled graph-ity, because it's using graphs to just try to describe the network that is space-time. And this idea here is to start with, in this case, I guess 9 quanta of space, themselves not spatial, and imagine a high energy network. Each of these links between the little quanta represents some kind of tension. So if it's fully interlinked, you have a maximum energy system. And it undergoes a phase transition. And links begin to pop, and that network that we started with resolves itself into something more that's like space. So in this teeny little Cartesian grid, you have you can put a metric on this. You can assign coordinates to the positions. There's distance relations that you have here. And this toy model can describe kind of in a loose way what happens in a lot of these quantum gravity theories, such as string theory, that you basically get a phase transition from a non-spatial to a spatial system. So space emerges in that particular sense. And by the way, that highly interconnected network at the beginning might be taken as a model for the interior of a black hole or the universe before or at the Big Bang. And the low energy universe we live in today might be more like that. And I'll come back at different points in my remarks to different types of emergence phenomena. So entanglement, and I am going to talk a lot about entanglement, seems to be really crucial to this process of emergence in interesting ways that have been emerging, so to speak, in the past few years. So I wanted to kind of back up and give a kind of historical set of remarks. In retrospect, it should be obvious that entanglement would be important to quantum gravity. It's quantum gravity, after all. But what's interesting sociologically and historically is that entanglement really was never considered in the realm of the quantum gravity theories. When people said quantum gravity, they were talking about discreteness. So they equated, in other words, quantum with discreteness, which is problematic, but that's kind of what the thinking was. Uncertainty, there were quantum fluctuations, even quantum superpositions of geometries. But the word entanglement, quantum entanglement, was never really in there, which is kind of strange. The specific connection between entanglement and gravity really comes out of the work of Jakob Bekenstein and Stephen Hawking in the 70s on black hole entropy. So Bekenstein's idea was that if you look at general relativity theory and apply it to black holes, when you merge black holes, their area, the area of the overall system, never decreases. So area is kind of acting in the same sense that entropy does in thermodynamics. So a few months ago, I would have had to concoct an example of this, but we have an actual physical observed example of this in the recent discovery of gravitational waves. So GW 150914. And I'm not claiming, by the way, there's quantum gravity, didn't see in that, but just in terms of illustrating what the area law is. So we've got according to the gravitational wave signature, there were 2 black holes that merged. Actually, the fact that the black holes were fairly large in mass is itself kind of an astrophysical mystery, but one was there's an error bar on this that I'm neglecting, but one about 35, 36 solar masses with a spin that's 30% of its maximal possible spin. and it merged with a slightly smaller black hole. And according to the area law, the final black hole had to be at least 45 solar masses. And the actual precise value of the mass would depend on what spin that final state had. And in the observations that were done, actually, hooray, it did not violate that relation, and we actually had a black hole at the end of about 62 solar masses. So interestingly, roughly three solar masses of energy was emitted in the form of gravitational waves, as opposed to up to 20, which would be allowed by general relativity theory. So let's just pause for a moment and reflect on the interpretation of the area law. First of all, it's kind of weird that there would be any limit on what happens to why, for instance, why couldn't two black holes merge and give off everything in gravitational waves? So it wasn't entirely obvious why there should be any kind of law at all here. And certainly it wasn't obvious why, it wasn't a priori obvious back in the 70s why area would be the defining characteristic here. And yet that's what relativity seems to say. So as Bekenstein argued, area is acting sort of like the entropy, or somehow related to the entropy of a black hole. Now classically, black holes have entropy is meaningless. We're talking about a black hole. A black hole classically doesn't come into equilibrium with its surroundings. It just swallows stuff in. It basically has a temperature of absolute zero. So Hawking then, if you're familiar with the story, Hawking then came along and showed that when you consider quantum field theory and the horizon of a black hole, the black hole actually has a non-zero temperature and a finite number of degrees of freedom. So the picture we have today coming out of the work of Hawking is something like this, that roughly each Planck area on the horizon of the black hole corresponds to 1 bit. Actually, no, I guess 1 degree of freedom. And then you describe the whole thing using a lot of bits. Now, a lot of this is, again, familiar, but I think it's worth pausing again to reflect on the interpretation of it. This is kind of what I see as my own job as a synthesizer here. General relativity is a theory of a fundamental interaction. It's not a theory of, at least it wasn't formulated to be a theory of thermodynamics. So, yet it knows something, if I anthropomorphize the theory, something about thermodynamics. And second, the implications of this kind of work went way beyond black holes, because any vacuum state in quantum field theory, and black hole basically is a vacuum except for the singularity, most of it is a vacuum. Any vacuum state will have this enormous complexity to it. Okay. Continuing my kind of historic review, from the work of Hawking and Bekenstein, the thinking kind of branched into two directions that then bring us to the present day. One was the direct study of black holes and horizons in a generalized way, and the other was the holographic principle. So let me start with the horizons. Bekenstein and Hawking had shown that black holes have entropy, but it wasn't clear at the time what the entropy was of, what kind of entropy we're talking about. And it was Raphael Sorkin in the early 80s who said, aha, it's probably entanglement entropy. That's the issue at black hole and more generally around these kinds of horizons. So the idea is that the black hole is defining a region. You then trace over the rest of the universe, and you get an entropy out of that, and that is the entropy that you assign to the area law. The nice thing about this is it gives you naturally that area dependence. Here's a nice graph that I got from Lenny Susskind. If you imagine this line being the horizon, and you, in your quantum field theory, kind of have this particular model that you have basically bell pairs straddling the horizon. The entropy, and because in a continuum theory, you can go down arbitrarily small, close to the horizon. In a continuum theory, the entanglement entropy is dominated by those very short wavelength modes. So it naturally gives you an area law. The area of the horizon will determine what the entanglement entropy of the black hole is. So it naturally kind of gave you the Hawking idea. By the way, there's a symmetry argument that I've heard. I'm not sure how valid it is. I'd be curious about your opinion. That because the only thing these two regions, interior and exterior of the black hole, share is their horizon, is the interface between them, the entanglement entropy must be proportional to the area of that horizon, just by kind of symmetry. I'm not sure how valid that is. I think it probably depends on what you assume about the cutoff here. So building on that work, Ted Jacobson in the mid-90s suggested, and he was really the one historically, this is just before the holographic principle was gaining some traction in physics, he suggested that there's a connection between entanglement and gravity. He really put it on the map. And the idea is that thermodynamics will relate energy to entropy. Just basic. And in fact, Jacobson tells me he got the idea of teaching undergraduate thermodynamics. He kind of had this brainstorm while teaching Clausius rule of energy being related to entropy. Entropy is related to geometry because of the horizon area. So energy is related to geometry. And that, you actually do that. You can derive Einstein's field equations in relativity theory just by thermodynamic logic. Here's kind of an intuitive picture for what's going on. That light rays, depending on the geometry in which they propagate, light rays will either converge or diverge. So the area that they span will increase or decrease, and that can be associated with an entropy. And you can relate that to a flux of energy and thereby get a connection between energy and geometry. Hence, general relativity theory. And it's remarkable, actually, you do get the Einstein equations out of this kind of thinking. I should say, though, that Jacobson, if you read that early paper of his, he's actually backed off from a lot of the claims that he made. He doesn't see this as a full derivation of gravity, really, anymore. He just sees it kind of as a consistency check. But historically, it was important for connecting entanglement to gravity. Okay, so let me go back to black holes. So the entanglement entropy of the event horizons are kind of a physical partitioning of the universe into the interior and the exterior. And if a particle falls into a black hole, you can never recover it. You can never put it back through your interferometer and get fringes. Initially, you might think, well, there's nothing terribly unusual about horizons in that respect, because your photon might fly out the window and go off at the speed of light, and you still could never recover it and bring it back and get your fringes. But the black hole is strange because it evaporates. That actually gives you the famous information paradox. By the way, even in Scientific American, we often describe this, even Hawking himself describes it as, I drop an encyclopedia into a black hole, I lose the energy, lose the information. Actually, I still have the energy. I lose the information in the encyclopedia, how bad that is. But classically, that's not an issue because you can always have a copy of the encyclopedia. But it becomes an issue when you consider quantum information. So here's the basic picture here. I got these slides from Samir Mathur, who's one of the first people to think about what I'll describe in a minute as the firewall paradox. You can start from your intuition about pair production in an electrostatic field. The potential between these plates will pull out, will cause a pair production process here of just of charged particles and will flow through your circuit. Something similar to that is happening at a black hole horizon, where the gravitational field is, in the kind of Hawking picture, is pulling out these Hawking pairs from the vacuum. And this is just a heuristic picture, so we don't want to focus on it too much, and it's also a discretized picture. But the point being that the two pairs being produced in this process are entangled. You get this happening, therefore, over the course of the lifetime of the black hole. More and more entangled pairs are being produced until the black hole just poofs and goes away. And then you're left with a bunch of particles that are entangled with, well, with nothing. And that's kind of the problem that the information paradox poses. Now, this overall process is therefore non-unitary. It's irreversible. I can't wind the whole thing backwards. Now, if you think unitarity is an important physical principle, you've got to figure out what's wrong with this kind of argument and find what other assumption has to be dropped. And lo and behold, the assumption that usually is dropped here is locality. In fact, that's one of the only other assumptions going into the argument at all. And what's interesting here is that you'd be giving up, in that case, if locality really does fail in black holes, you're giving it up in a low energy regime. You're giving it up at the horizon. We could actually be in a black hole right now, out at its fringes, and we would still see low energy physics around us by the equivalence principle. So this is a failure of locality in a regime where we expected local theory to hold. not at the Planck scale, because everyone knew the Planck scale was a problem. This is a very different problem. Now, there are different ways people have talked about locality failing. One is simply that it's a true action at a distance of some sort between the interior and exterior of the black hole. Giddings at Santa Barbara kind of argues for that. Of course, if you have action at a distance, you begin to wonder about causal paradoxes and such like. So people try to resist that. So one idea that Lenny Susskind developed was this idea of what he called black hole complementarity. And it proceeds from a simple, though in retrospect incorrect, observation that if you're falling into the black hole, you see a qubit. If you are safely outside the black hole, you see the same qubit, but somehow encoded in an interesting and scrambled, as he put it, way. So you seem to have the same qubit in two locations, but no one observer could see that discrepancy. So operationally, you wouldn't see the discrepancy. And Susskind's argument was, well, we don't see a direct paradox. What's really happening here is we're viewing the situation in the wrong way, that we think the qubit exists in two separate spatial temporal locations, but actually space and time really are failing us here. And we shouldn't be ascribing space-time locations to these qubits. And therefore, there's no issue with cloning or anything like that. This, by the way, really violates, certainly violates an idea of space-time theory, but it violates our sense of locality in its very basic sense of localizability. Namely, I can't localize my physical information in any one place. So and I think Scott Aronson spoke about the Firewall Paradox in November or whenever it was. So I think it's interesting, and I'll review it at kind of an elementary level. It goes back to Mathur's work in 2009, and then the work of Bolchinski and others in 2012. And they basically argued that complementarity, the thing I just discussed, doesn't solve this problem. And they used kind of an argument about polygamy of entanglement. So because of the proposition that the black hole is actually a vacuum, that no infalling observer would see anything but just vacuum, you need to entangle the pair-produced photons, the one that went in toward the singularity and the one that went out, and maximally entangle too. And if you presume that the overall process of black hole formation and evaporation is unitary, you need to entangle maximally all the photons that came out, or somehow this is entangled with a composite of the others from which you've extracted the information. So you've got maximal entanglement of a single, well, I didn't show it, maximum entanglement of a single Hawking quanta with two other quanta or set of quanta, hence the idea of some kind of violation going on here. And they actually, in the paper by Morolf and Paczynski and Sully and Elmeri, worked out that you violate strong subadditivity of entanglement entropy. And I'm not going to go through that in detail. I've actually spent a lot of time trying to get the slide to animate properly, but it doesn't really matter. You get actually the inequality goes exactly the wrong way. So again, assuming that you think unitarity is the principle in physics you need to preserve, and there are arguments that you can give for that. We need some kind of reversibility in our fundamental, time reversibility in our fundamental physical laws. You have to question one of the other assumptions, and the one that was a question in the 2012 paper was the entanglement of the infalling and outgoing Hawking pair. So if they're not maximally entangled, or even perhaps entangled at all, you don't have a vacuum in a black hole. You've got instead a highly energetic region. That's the word firewall. That's the idea of the firewall, that when you, God forbid, fell into a black hole, you would strike the firewall and be incinerated at the horizon, not even falling into the black hole. In some of the models that come out of string theory, what happens is that there actually is no interior to the black hole. That we think is a region of space in there, but actually is no space in there. It's just that space ends at the horizon. And there's different ways you can understand that. One goes back to my idea of a phase transition, that you can actually have an instability during a collapse of a star. The tunneling process, this is all string theoretic ideas. a tunneling process to change the topology of space-time, and you get a little hole in space-time. Space-time kind of becomes a donut in that context. There are actually many other ways to do it, and one comes out of some of the work in there's different ways to understand this so-called paradox. To get rid of the firewall, and one is to look at the complexity and the quantum complexity, really the computational complexity of the act of understanding where the qubit is and all that outgoing radiation. And that's the work of, I guess, Harlow and Hayden. And they argue it's actually impossible to decrypt that information, certainly before you fall into the black hole and die as well. One thing I'd love to get your reactions to is some people being Sabine Hassenfelder, argues that you can actually structure the entanglement to satisfy both needs of the vacuum and of the unitarity of the evaporation. Hawking himself, he had a recent paper with Andy Strominger and Perry, arguing that the vacuum itself can preserve the information, that the vacuum state is degenerate, actually is capable of multiple states, and you can kind of have the information encoded in it. Anyway, it's kind of interesting debate, and again, is an opportunity for collaboration between the quantum information and the quantum gravity sides. So let me go into the other kind of branch that came out of the work of Bekenstein and Hawking, namely the holographic principle. The proposition here is that black hole entropy scales with area. And at Hooft in 1993, said, well, anything can be made into a black hole, so the entropy of anything is limited ultimately by its surface area. The black hole, in other words, is kind of the maximum entropy state of matter in general. It's not just its own little weird thing. And that clearly violates our expectations, certainly from field theory. In quantum, in a continuum field theory, of course, you have an infinite number of degrees of freedom in any volume of space. But if you kind of cut it off, you would expect the number of degrees of freedom to scale up with the volume. And we're being told from gravity theory it's scaling up with the area. So you've reduced vastly the number of degrees of freedom. And here's a little picture I just made to dramatize that. If you here is just a volumetric scaling. I think I put this little ball, I put 10 dots, and then I increased it, I increased the radius tenfold, 1,000 times per volume, 1,000 times per dots. But if you do that with the area scaling, you have scaling up just 100 times. And what I'm trying to show here is that you have a lot fewer degrees of freedom than you would expect coming in a black hole. There's a vast reduction of the number of degrees of freedom through means that are unknown, at least so far. Another way to put it, by the way, and this is Ed Hooft in the 93 paper said this, another way to think of it is all those zillions and zillions of dots are massively correlated with one another. And he actually thought that would be related to EPR correlations. That actually was one of his motivations for that project. This area scaling is obviously quite reminiscent of a hologram, hence the term holographic principle. Here's kind of the modern way of viewing it. You have two theories describing the same system. One is just a quantum field theory, not just a quantum field theory. It is a quantum. It's actually quite a complicated quantum field theory, but living without gravity in flat space. And then kind of the interior, or the other system, is a quantum gravity theory living in some higher dimensions. It actually lives in one higher dimension representing the radius, and then there's actually some compactified dimensions as well. And this is string theoretic ideas. So there's a lot of those little compactified dimensions. This is the most well-developed idea of emergent space. And not time, by the way. Time does not emerge here. Time is the same on those two theories. So emergent space. This is the best developed idea we have coming out of quantum gravity theories of emergent space. So the structure of this field theory on the boundary somehow can be interpreted geometrically as an additional dimension of space, like the interior of this little ball. Not only, by the way, do you get emergent space, you get emergent gravity. That's kind of what made people excited about this, is you can start with a theory without gravity and bootstrap a theory with gravity in the middle. Let me digress for a moment, because I think you guys might actually find this fun. So theorists have talked about the holographic principle for, well, since, I guess, the early 90s, and certainly since the work of Malta Sane in 97. But I always wondered, can you actually look at a real, honest-to-God hologram and kind of see something like a holographic principle applying there? So last summer, I actually went up to a holography studio, and we put together this little experiment that might be fun to do with students. So what we did is we took this kind of funky hologram. It's just made of pencils. It just shows 2 rows. I have a better image of it in a second, but it shows 2 rows of pencils. And normally you would illuminate it like this, just backlight it with a laser, and the pencils would appear to be behind the film. So what we did in our little experiment is we flipped the film around. We actually, doesn't show here, we actually turned this here. We back illuminated the hologram so that the image would be formed in front of the film. And it was sort of like going from a converging to a diverging lens. You wouldn't actually see that image with your naked eye, but what you would do is you put a screen, like we took, I guess, a piece of plexiglass, and put it in this aluminum mount and actually put it in front of the hologram. And their idea was to do basically tomography on that holographic image and see what we would find. And this is what we found. So we masked the beam using different sizes of beam size. So we started off just by shining the laser straight at the hologram, just a point. And we took a look at what kind of image we saw. And actually, it didn't come out too well. I'm glad these lights are off here. I can show you on my screen later if you're interested. But basically, the entire image is in focus here. And if you move that screen backwards and forwards, you don't see any difference in it. The hologram, in other words, when you illuminate just with the dot, it's acting just like an ordinary photograph. But if you widen the image, if you broaden it with that mask a little bit, you start to get a defocusing of part of the image. And all the way to the end, which it's easiest to see here, you are focused just on the front line of pencils on the hologram, and the back line is completely defocused. So, and if you, I don't show it here, but if you move the screen back and forth, you can bring the back line into focus, and the front line becomes defocused. So in other words, I've shown the emergence of a sense of depth in the hologram simply by changing the degree of illuminating the hologram. I mean, it's pretty standard, having to do with how holograms are created and what they actually mean. But it actually shows you, in a sense, the holographic principle with a hologram. The way you can think of it in the quantum gravitational case is you're activating, in a sense, more and more the degrees of freedom, and that creates a sense of depth, that you have another dimension emerge from it. The information, and this is important for the quantum gravity case as well, the information in that dimension that's coming out perpendicular from the screen here is non-locally encoded over the entire surface of the film. And that's true in the holographic case too. The radial dimension in the holographic principle is encoded on the entire surface of the boundary of the universe, which is an infinitely large surface. So going back to gravity, the big development, I think, just from my interpretational view here, from my outsider view, in the past few years is a recognition that entanglement is extremely important in understanding how holography works, the gravitational version of holography works. So the holographic duality, the logic of it is that it takes a weakly coupled system and relates it to a strongly coupled system, and it goes both directions. So if you have a semi-classical state in the interior of that toy universe, that kind of ball, you have a highly coupled system on the boundary. In other words, you should have a highly entangled system on the boundary. And there's kind of an elegant argument that Mark van Ramsdonk in Vancouver shows for this. So suppose you have a product state of, well, in this case, it would be of a conformal field theory, but it kind of doesn't really matter. A product state, each of which will be holographically related to a universe. So what you have when you have a product state is you have two universes that are completely disjoint from one another. But then what you can do is you can imagine, well, what if I have an entangled state? in that case, in this particular model, it corresponds to basically a wormhole between your two universes. And one way you can see that is if you imagine tracing over either A or B here, you'd actually get a thermal state. And the thermal state within the context of the holographic duality actually corresponds to a black hole. So you've got kind of a black hole in both of these. They're connected by an Einstein-Rosen bridge. So von Römslang argues that this is crucial to understanding how space-time is integrated into a cohesive piece. If there's no entanglement, and he uses kind of a mutual information measure of this, if there's no entanglement at all, the proper distance through that wormhole, this is kind of your wormhole here, is infinite. But as you increase the degree of entanglement between two regions on the boundary, the proper distance measured through the bulk shrinks until you get down to a case where you've just taken two universes and merged them into one. So you just have a single geometry, kind of no wormhole there anymore. Now, just to emphasize the point, the role of entanglement here is quite different from the role of entanglement in what I discussed earlier, because the entanglement is in the boundary theory. This is in the middle, this universe filled with stars and galaxies and humans and everything else, according to this idea, is a classical universe. It's the entanglement occurs not in our own spacetime, but in a different spacetime that is dual to ours. So what's interesting about this is that understanding entanglement seems important to understand what the interior geometry is and the connectivity that it has. In fact, the fact that you have an interior geometry depends on the entanglement structure in this field theory. And that was kind of formalized by Ruan Takayanagi, I guess it's 10 years ago now. Basic idea is you start with a patch on the boundary, and you can calculate the entanglement entropy of that just by tracing over the complement. And then you consider kind of a soap bubble that you've blown, so a minimal area surface extending into the bulk. The entanglement entropy here gives you the area is given by the area of the soap bubble. So those two are related to one another. In fact, the degrees of freedom in this are also given by the area through the holographic duality. So again, entanglement is crucial to understanding the geometry of spacetime. And von Römslang has actually been able to reconstruct general relativity, at least at a linearized version, from the constraints that you would place on entanglement structure here. You can actually derive GR at some approximate level in the bulk. Ted Jacobson actually had a paper, I think, in December, where he went a step further. He got the full nonlinear GR in the bulk. It's worth looking at his paper, and from kind of additional constraints you would place on the entanglement out here. Now, I've spent a lot of time trying to get this slide animated properly. The geometry, this geometric consideration actually lets you understand the strong subadditivity just geometrically. And I'm probably not going to go through this because I might screw it up. But it's actually kind of cool how it works if you've never seen this before. I can go through that later. The fact is that each of these is a minimal area surface. Well, anyway, I'll go through that later if you're really interested. So the question is, what is the entanglement structure that you need to really reproduce that interior geometry? And this is where people make contact with condensed matter theory. Brian Swingle, I guess he's now at Stanford, but had been at Harvard at the time, was a condensed matter theorist, and then had this kind of brainstorm and talking to people that actually he could apply his ideas to these quantum gravity situations as well. So he imported into quantum gravity theory this idea of entanglement renormalization. And it's actually quite similar to renormalization group in field theory. You kind of go up in size or energy scale, each point aggregating at each level of the system, aggregating the degrees of freedom. That's what these symbols represent. You're kind of aggregating in a hierarchical sense the degrees of freedom, and in this case, actually the entanglement structure of a condensed matter system, like something at a quantum critical point. And what's cool here is you can give a geometric interpretation of entanglement. So here's kind of a little animation that I created based on one of our artists at Scientific American. So you can start to pair up, imagine these are bell pairs, and then you can go to entanglement of progressively larger systems, even larger, and you can kind of imagine the scale of the system that you're entangled acts as a spatial dimension. You can kind of give a geometric interpretation of that entanglement structure. The condensed matter people, of course, love this because they can solve, and I don't know if any condensed matter people are here, but you can solve, understand huge networks of entanglement by using gravity theory. And sometimes you see direction going the other way, where condensed matter results can be brought into gravity theory. Anyway, again, for me, it's just cool that you can understand space, the structure of space, by looking at entanglement. Because on the face of it, entanglement seems to violate our sense of space, but somehow maybe it's implicated in the creation of space. So I'm presuming that there's a lot more scope for crossover work between the two areas of information and quantum gravity. And I don't pretend to be an expert on this, but I hope I haven't offended the experts too much in my remarks. Thanks.